Welcome back. Last time we looked at cleaning up our code and actually using a C structure to reorganize the entire code. So what we're going to do now is actually consider the next reorganization. And that is basically separating anything that has to do with reading and writing. Why do we have all this statement interspersed with the rest of the logic? They should really be modularized. Remember, writing small functions that do one thing is really valuable, because if there are no side effects and they just work in isolation, convincing yourself that these routines implementation are correct and therefore you can abstract them away when you're hunting for other bugs is extremely valuable. So that's what we want to do. We want to be in a position where we can abstract away details that are irrelevant, and the best way to do that is to put them in functions. To do good abstractions, these should be short. That's the name of the game. That's what we want to do. We want to have two functions to just read and write everything. So let's take a look and see how we do that in the code. If you recall, last time we just had our type def, right? That's where we should be. We just had our type def. Going back to the top, that's exactly what it looked like. So we had our struct student, and then we started using our student. Now what I'm going to do is go and pick up a third version of the program, which is here. And as you would imagine, it starts in exactly the same way, right? I still have my structure for student, which is here, same definition. Then now, rather than actually starting main, I have some function. Wait a second, let's go see the main program and take a top-down view, and then we'll start drilling down. So my first approach is drill down from the top and see what this is like. So I'll go at the end of the program where I have my main program, and main has undergone a dramatic change. Main is now this very simple thing. It calls read students and get back, ta-da, a student, st, and then it calls student report on st to actually, well, print the grade report. What would you expect? So now main is absolutely clear as day. We're calling a function, getting a student, that student exists on the stack, we're invoking student report on it. Clearly that should not modify the student, by the way. We know that we're just printing, we're just reporting, so that should be dealing with the student as if it were a read-only thing, and then we return 0 because that's what main expect. Very short specification, 3-line, that's a function the way I really like them, so we shouldn't have to worry anymore about this. This is quite nice. Now let's take a look at read students and see what it does. So back to the top, and now let me center read student. Now the first thing you notice is that I'm starting to get where I want. Read student is a function that spans here to here. It's one screen. I can see everything in one shot and see exactly what's going on. With the name, I already know that it's only supposed to read a student data and not do any kind of calculation or printout. It's all about getting input, maybe putting out a prompt, but that's about it. There is nothing else in there. So what do? I declare a student. Well, of course, I gotta do that. But you're thinking, well, but I have to return that student at the end. What's going to happen? Well, remember that return value will be copied on exit. So since I have a student and I'm returning a student, not a student pointer, not a student reference, I'm returning a true student, then the student that I have here will be copied into the return value when I actually return. If that student takes 200 bytes of storage, that means copying 200 bytes of storage, because clearly that student lives on my stack. That is, when read student terminates, the student that's embedded in the stack will go. Just a quick explanation, a reminder of the stack. This is my stack, right? This is the function main up here. This is where we were. This is main. And inside of main, there will be storage. And I'm going to even enlarge main a little bit. There will be storage for a student. We've seen that it's called st. St will be on the stack, and it's an object, the same kind of object I was describing earlier. It's a structure with a string, 2 double, and a vector of homeworks, right? So it's something that looks a bit like that. I think that's how we drew it last time. Name, 2 double, homeworks. It's on the stack. This is where I am when I'm inside main. Now at the beginning that student is uninitialized, but we call read student. So now we enter a frame for read student. So here is read student. And as you would expect, read student provides storage for students. So in here, there is, remember always when we do that, right? So this is my student here. This guy will actually have some space for representing its argument and whatnot, some management data. So here maybe there is some management data. This would be for the argument, so I shouldn't have drawn a line here. Let's just say that these are the arguments. Now, as you know full well, there are no arguments to read student. We've seen that, so that should be empty in reality. Then there is management data down here. And then finally, I have a student, so let's draw him. In here on my stack, I have another structure that has a name, 2 double, and a homework. That's the student in the routine read student. Right? So all the input that takes place here goes into that storage. When I reach the last statement, I say return st, which means I take this entire storage, or C++, I should say, takes this entire storage. Let me change color. Hopefully that one will be readable. It takes this entire storage here, and then it goes and writes it over here. Because that's what we're supposed to do. We're supposed to take the structure and return it. So there will be a big copy that's happening automatically. Notice that the heap is not involved. There is no memory allocation. Everything is happening off the stack. So that's what I want you to remember here. My return value can be complex type. They don't have to be scalars. And if there are objects that lives on the stack, upon return, the entire object is copied. Now, how is this copy happening? Well, C++ provides the mechanics to do it, but the beautiful thing, the even better thing, is that you can change that. You can define exactly how the copying happens, and we will discuss that at length when we discuss classes and constructors, because there is something to do that, and it's called, remember the name, but we'll see it again, a copy constructor. That's exactly how it's done. So now, let's take a look at the code. Nothing really special. Here, we are actually printing the prompt. Please give me your first name. We're reading it. We're printing out, hey, good morning, blah, blah, blah. Please enter your midterm and final. We're reading them. Again, we're putting them directly in the structure. So this code is completely straightforward. We're saying, oh, enter your homework, my local variable. Now it's a local variable of the function read student. It does not even pollute the main function. It's completely localized, and you don't have to worry about X anymore. Then I have my while loop that says as long as my input stream is not empty, let's read an X, let's add it to the vector, and when I'm done, I'm returning the student. Simple, beautiful. Once this is done, then the student report, remember it's the second part, as expected, you directly see it here. Once again, a very short function, so I'm getting to have modular code now, right? Every function holds in a single Emacs screen. This is much better. But something that's important, remember what we said when we saw main, which I'm going to put on the screen at the same time, is that the student we get from read student, when we print the report should be a read-only operation on the student. It's not supposed to modify the grade or do anything silly like that. So in order to enforce that requirement, the student that I'm passing, I'm making him const. It's a constant student reference. Now, why do I do that? Well, I could pass it by value, right? But if you pass a student by value, when the call student report happens, what's taking place? Well, you have a student up here. You calling the routine student report. It's a call by value, therefore the student needs to be copied on the stack. So I get to copy this entire thing in the other direction, in the frame of student report. It's a lot of copying, and since here all I'm doing is doing a silly printout, maybe it's a little excessive. So I can save myself the aggravation of copying and the cost that it carries by saying that it's a reference. So essentially I have the same as passing by pointer, but to make sure that you can't damage the object in the process, I make it constant. Now that it's constant, I know that nobody inside this routine can accidentally modify my student, and life is beautiful again. I get good performance, because it's like passing by pointer, there is no copying happening. And second, I get the correct semantics because it's impossible to accidentally modify my student. So I get the best of both worlds. Now the routine itself, nothing much has changed. Total, the loop to compute the total, declaring my size, computing my average grade, and then the normal printout, and we're done. And that's it. That's all there is to this program. So now you've seen that I've cleaned up substantially. I have 3 routines. I have my structure. The code is getting more readable, but maybe it's not as as it should be quite yet. So let's push one step further, and we'll do that next time by modularizing this even further. See you next time.